What is the common denominator between these companies? Klarna, Ericsson, NHS, this is the UK Health Service Agency, Goldman Sachs, WhatsApp, Nintendo, and Cisco. They all use Erlang in one form or another. I want to talk to you about how Erlang has empowered Klarna over the last 20 years to operate large financial systems with extreme requirements on availability and performance. Let's start with some history to sort of set the stage here. Kreditor was a Swedish fintech startup founded in 2005. And they had a single idea to make e-shopping easy, both for the merchant and for the customer. Kreditor changed name to Klarna in 2008 because Kreditor was sort of a boring name. And 20 years later, Klarna is a multinational company with millions of customers and thousands of merchants. Erlang was invented by Ericsson in the late 80s, and the purpose was to improve the development of telephony application. And the Kreditor engineers who started this, they thought that, well, telephone applications is sort of similar to financial banking stuff. So let's use Erlang. So what are these features? I want to take up 3 features and cover these and describe them how they work in Erlang. The first feature is scalability and distribution. Erlang made it possible to take their small initial prototype and scale it to a large production system which was able to support all the traffic that they sort of envisioned at the time. And the excellent support for distribution in Erlang meant that it was easy to scale the system up by adding more servers. Erlang's built-in support for reliability and fault tolerance made it possible to operate these systems with high availability and at the same time provide fast time to market for feature development through daily software upgrades. And Erlang's support for massive concurrency comes very handy when you want to be able to support several thousands of requests per second, and you don't want to pay for extremely large hardware. So I'm going to talk a bit about Erlang, but I'm going to just cover sort of the stage for what Erlang is. Erlang is a functional language with built-in concurrency, immutable data, pattern matching, single assignment, and dynamic typing. So now you know what Erlang is. This is the only thing you really need to know. Sometimes you will hear the term Erlang OTP. OTP stands for Open Telephony Platform, but it's largely irrelevant, the abbreviation. It simply means the core language plus an extensive set of standard libraries. I will not talking about much of the language itself here, but I will be showing some code examples, and I hope they will not be too difficult to follow. One feature of Erlang that might warrant a closer explanation is pattern matching. This is a very powerful mechanism to deconstruct and assign values. And it's a very common construct in Erlang. It is used everywhere. And it's been gaining popularity in many other languages, such as Rust and even Python, I think. So what happens here is that this is some examples of pattern matching. You have it looks like an assignment here, and you have a fully instantiated term here on the right. It's an OK tuple, and you have a partially instantiated pattern on the left. So this result here is a variable, which you can see because it has a capital R. So these are variables in Erlang. And if these patterns match, if they have the same shape, the pattern match will succeed. And all the variables on the left-hand side will be bound to the corresponding values on the right-hand side. So we can see what happens here with foo and bar. X will be bound to foo, and y will be bound to bar. So we get out x, y here. And if this doesn't match, if the shapes are different and can't be unified, you get an exception. So how many of you have heard of Elixir? Show of hands? Yeah. As you might know, Elixir is a language which is closely related to Erlang, and it runs on the Erlang VM. And it incorporates features from languages such as Ruby and Clojure. It's gained a lot of popularity recently, over the last couple of years. 5, 10 perhaps, to the point where it's in many cases more popular and well known than Erlang itself. However, I will not be talking about the language, but more about the Erlang VM. So most of the stuff that I'm going to say here will apply equally to Elixir. My name is Jesper Eskilson, and I worked with compilers and programming languages and debuggers for more than 20 years. First at Six doing Prolog, and then at Vertitech doing full system simulation software, and then at IR System doing compilers and debuggers for embedded systems. And since 2018, I work at Klarna maintaining and developing the CRED system, which I will be talking about later. This is a picture of me out skating on a frozen lake, which I try to do when it's possible, when it's cold enough. So let's talk a bit about scalability and distribution. Erlang is designed to be scalable. And this can mean a bit different things depending on who you talk to and what kind of context you are. But Erlang can be run on all kinds of hardware, from tiny bare metal such as the GRISP system to huge servers with terabytes of RAM. Klarna operates many Erlang services of varying sizes, from the quite small in the range of 50 to 100 megabytes to the very large in the scale of 100 gigabytes. And we've even had really gigantic services which consume like 1 to 2 terabytes of RAM. These are no longer around, I'm happy to say. Now, 50 to 100 megabytes may sound like a large thing, because depending on sort of what your context is, but these are systems that are handling large volumes of financial transactions. And by large, I mean thousands of transactions per second, sustained over like on average, and with peaks are much higher than this. So Erlang allows us to run these services with low latency and high reliability. And another aspect of scalability is that you can take your small initial prototype that the Keditor people started out with, and you can scale it up to a large production environment. And Erlang makes it easy to do this because it's fairly easy to get a lot of things done with a few lines of code. And the core language is relatively small, which is really nice. The syntax is not very, very complicated, and it has some powerful language features such as pattern matching and list comprehensions. And we found that it's easy to learn. 3 to 5 days of training is usually enough to get developers who have never seen Erlang up to speed to actually do real Erlang things in production. Distribution. The Erlang language and the runtime is designed to be distributed. And by distributed, I mean running on multiple servers at the same time and communicating. Erlang implements what is known as the actor model, where processes communicate by message passing only. And there is no shared state between processes. So processes encapsulate their own private state. This means that there is no need for lock-based synchronization, which makes it easier to reason about processes, about the behavior of a process. So I like to go into a little bit detail, because otherwise this becomes very abstract what distribution means. So Erlang runs on a virtual machine called the Beam, the same one as Elixir does. An Erlang system is one VM instance, and we call it a node in Erlang terminology. A distributed Erlang system is several interconnected nodes. And nodes have names, and they are identified by their name and their host. So given a name and the host, you can find an Erlang node in a cluster. So this is sort of the most tiny Erlang cluster you can think of. There is a node called bar and one called foo. And then we connect to it here with a function called connect node. So now these two are running in an Erlang cluster, and they can communicate with each other. Since distribution is built into the system and built into the language, process identifiers have their own data type called a PID. And these PIDs are location transparent, which is a very nice feature. This means that if you have a PID, you can send a message to it regardless of where in the cluster the process lives. And you can also name processes. So there's a name registry where you can register processes. And this looks something like this. So this is the Erlang shell. And the shell is, of course, just another process. So you can call self here to find the PID of the current process. And then you can register it under the name the shell. And then then you don't need to know the process ID of the shell. So how do you send messages? Messages are sent using infix bang operator. And the left side can be a PID, it can be a name. And the right side is the message to send. And these are asynchronous, so they return immediately. And they're quite fast. Messages are encoded using internal binary encoding, which is designed to be really fast to encode and decode from. So messages sending can be just as simple as doing this, or using the shell here. Or you can even send a message to a named process on another node. And you can send any sort of compound data type, lists, tuples, records, and so on. And they will be encoded automatically. So on the receiving side, each process has a mailbox, which is built into the system. So you don't need to create it or anything. And this is to pull the key or to receive a message from your inbox. You use the receive keyword, and this is a built-in keyword in the language. And you use pattern matching that I mentioned to select the incoming message, which is really nice. And they arrive in order, of course, but they can be processed in the order you want. So this is a sort of simple thing. You do a receive here, and if there is an incoming message which matches this pattern, do something, x. Then pattern matching will bind x to the corresponding value, as if you would have done one of these pattern matching equals assignment operators. So this is a very nice and declarative way of saying, okay, now I'm waiting for this, and if this message comes in, I want to have these parts assigned to the various parts of the message. One thing which is important to do, to be able to do when you're dealing with fault tolerance, is that you need to be able to know or detect when a process terminates. And this is difficult and error-prone to implement manually, but fear not. Erlang has this built into the VM. There is a functionality called monitors where you can register a process, where you can monitor another process, and you will get a down message when the process terminates into your mailbox automatically. So this is one of these system messages which are sent. So you can spawn in your process, you monitor it, and then you wait for the process to terminate. And in here you can do, of course, other things as well while you're waiting. And when the process dies, you will get one of these down messages. So this is really nice, and it's used to detect to handle crashing processes. So now we get into this reliability and fault tolerance, which is, I think, one of the interesting parts of Erlang. This is probably my favorite Erlang quote by Joe Armstrong, who was inventor of Erlang. If Java is write once, run anywhere, then Erlang is write once, run forever. Perhaps counterintuitively, we begin by crashing. So this is going to be a theme in this talk. So I attended a talk yesterday, and this was, have you tried turning it off and on again? It came up in that talk as well. So now I'm repeating, have you tried turning it off and on again? It is a well-known fact that software errors tend to go away when the system restarts because, well, software, when the system gets to start from a known good state, chances are better that things will actually work. Erlang builds its let it crash philosophy on this fact, where instead of trying to handle errors by catching them and trying to recover coding retry loops or something, we just let the process crash. And then we restart that process and see if it works better. If you just let the process crash and start a new process to do the same thing again. If the process persists, we restart a larger part of the system and see if that works. So we escalate to a larger part of the system, and so on. And this is a very powerful way to deal with software errors and to recover and escalate when problems appear. Restart, recover, escalate when needed. This is another one of these mantras. Restart, recover. A fundamental concept in Erlang when it comes to reliability and fault tolerance is the supervisor tree. This is in many ways the secret sauce of reliable Erlang systems, a well-crafted supervisor tree. A supervisor tree is a hierarchical arrangement of processes into supervisors and workers. Workers, as you might suspect, perform computation, and this can be things like handling an HTTP request. Supervisors monitor workers and restarts them when and if necessary. And to make the tree thing complete, supervisors are also workers. This means that a supervisor can decide that, this process can't be restarted safely, it just keeps crashing. I'm gonna crash myself and let my parent deal with it. So this is a supervisor tree. An application is a part of an Erlang system, and it has a root supervisor here, type 1 here, and then it has a bunch of other supervisors and workers down here. And one of these crashes, the supervisor here can decide to, I'm going to restart that. And if that doesn't work, it can decide to, I'm going to get up and crash. And then this one, the top level supervisor will have to decide what to do. So, a supervisor is responsible for starting, stopping, and monitor workers. And the purpose is to keep them alive by restarting them if necessary. And we used Erlang monitors that I talked about to get notified when one of its worker processes terminates. And we can escalate to the parent supervisor. For example, if a process crashes too frequently. So if a process crashes like within half a second 10 times immediately, then the supervisor can decide that, there's no point in really restarting anymore. I'm going to give up and crash. So, and then much of Erlang stability, or the stability of an Erlang system relies on having a well-crafted supervisor tree. Too shallow trees might cause too much of an application to restart. And too deep trees are, as you can expect, difficult to debug and they're difficult to reason about. Supervisor trees need to be able to limit crashes to affected parts of the system. And they need to be able to protect essential processes. You may have processes which are not allowed to restart. They may deal with something which is really, really critical and cannot be restarted safely within the same process. And the same application may have a bunch of other processes that you really don't really care about. They can just be restarted whenever. So the supervisor is responsible to make sure that those less important processes don't crash the more important ones. So I'm going to take a short example. An application which needs to talk to a database. The database is unreliable. It may be down from time to time. We want the application to gracefully degrade, so it's able to say that, the database is down, sorry, try again later. And we want to be able to automatically come back up when the database is available again. And in the terms of Erlang and supervisor trees, this may be just as simple as a one-liner. Connect to database, and then we match on a successful result. This is nice, clear, declarative code. There's no manual exception to throw. Pattern matching will take care of this. And pattern matching will also tell you the exception will contain the term the error term which actually failed to match. So if the database is down, you get an error term and the process crashes. So the supervisor detects that the process crashes, the database is down. The supervisor can say that, I'm going to wait 10 seconds and then restart. And this may keep happening. And the supervisor may try to, I'm going to give up because this is not going to work. And each restart of this database worker thread is its own process. So we know that there is no cleanup required. So the worker will start from a clean state. So this is sort of a supervisor implementation in Erlang OTP. This is built into Erlang OTP. So if you want to use these supervisors, you just need to specify a short specification file and a supervisor module. So you don't need to write this code yourself. And when it gets one of these down messages, it'll possibly wait a bit, and it'll try to restart the worker, and if that doesn't work, it might escalate to the parent. So let's summarize supervisors. It's a built-in feature in Erlang. It's tried and battle tested. So this is it's been in use in the industry for 20 years or more. It provides you with a uniform way of handling errors, restarts, and escalations by letting the supervisor define how the process and the application starts and restarts, and the worker can define invariants instead of having to code exceptions and retry loops. So the worker can just define, this is the way it's going to be, and if this is not happening, I'm going to crash. So this is a nice way to decouple error handling from program logic. The second thing about fault tolerance I want to talk about is hot code upgrades. And this is probably one of the, I think it's more or less a unique feature in Erlang and Elixir. It means replacing the code in a running system without stopping it. And this is not just about loading code. So hot code loading is sort of, yeah, we can do that. But we also need a way to we need a well-defined way of transitioning old processes to new code. So processes that are running in the code. And if you try to load new code, then what? When will each process start executing this new code? And what if the new code isn't compatible? What do you do then? This is natively supported by the VM from the start. This was a sort of requirement when Erlang was designed and implemented. So this works like this. You have each module in Erlang can exist in two different modules, two different variants. The current one and the old one. And this is sometimes referred to as slots. So there's a current slot and an old slot. When a module is first loaded, the code always becomes current. And when a new instance of the module is loaded, then as you might expect, the current one becomes the old one and the new one becomes the current. And these two modules are fully valid and can be executed concurrently. So they are not like, the old one isn't like less of a module. So they can communicate with each other using processes, like message passing. If a third instance module is loaded, then the old one is purged. It's unceremoniously killed, or rather, it's removed from the system and any processes executing in it is terminated. And this can be confusing the first time you try it out, but it's sort of the only way to deal with this. We can't have like lots of processes running around in 5, 6, 7 versions of old code. And then the same thing happens. Current becomes the old one and the new one becomes the current. So how do we transition code from running in old code to running in new code? And this is quite simple. Processes transition by doing a fully qualified function call. If you do a fully qualified call, you will always end up in the new version of the code, regardless of if there is an old version available or not. Local call will stay in the same module. This means that any call from outside the module will always go into the new version. So the only ones who can execute in the old modules are processes which are already inside that module. And together with tail recursive loops, this allows for a quite elegant way of allowing processes to upgrade themselves or upgrade on demand. So assume that we have a process which is running this loop function as a starting point, and they're waiting in a receive loop. They're doing a receive, and whenever a message comes in, they do stuff, and then they call back the loop. If they get the special message code switch, they will do a fully qualified call to themselves and upgrade to anything new. And this is idempotent, so you can send the code switch message to all the processes in your system, and they will just automatically work. And if there is no new code, nothing happens. So, sort of obvious benefits, this allows for 0 downtime upgrades, even with single node systems. So if you're running an Erlang system which just consists of a single node, you can still get 0 downtime upgrades. And At Klarna, we use this as an incident mitigation tool, which allows us to deploy urgent fixes with a very quickly, which is very nice when you have an incident which is actually costing you money by the second. Where it's like every second is like another 1,000 purchases which are lost. So that's a really good thing. It's a really nice testing experimenting tool when you start developing with Erlang and you get used to having hot code upgrade. You get very annoyed when you suddenly start doing Rust and you discover that, oh damn, I want to recompile, but I have to I have to stop my program. That's silly. There are of course pitfalls. I'm going to take the third one first because it's sort of obvious. Monkey patching means that you can load any code at runtime. And of course, you can shoot yourself in both feet at the same time. Or as Bjarne Stostrup said, as described in the JavaScript talk this morning, you can blow your entire leg off. But the first one, which is sort of non-obvious, is that the process has to make one of these fully qualified calls. You cannot have a process which is stuck in a local loop, a local tail recursive loop. It'll just keep running there all the time. And it's even the case that we've had an incident at Klarna recently where we had a process which was stuck in this, which was not upgraded because we didn't detect this. So there's actually a PR out now for Erlang to add a compiler warning if the compiler can detect that you have a process which is only doing local calls. The second one is compatibility. The new module must be compatible with the old, so that when you do the upgrade, when you make the migration call into new code, the migration call will work. So you can't the migration call just suddenly required you to this parameter here just has become an integer instead of a string. And then the old code comes along and tries to call into that and crashes. Yeah, and then this monkey patching thing, loading arbitrary code at runtime, it's both a curse and a blessing. So let's talk about massive concurrency. Concurrency is everywhere in Erlang, and this is something that you sort of strikes you when you start developing in Erlang, and it's part of the language design. Processes are first-class citizens, and the VM supports very high level of concurrency. And the standard library uses concurrency everywhere, so you better get used to things running at the same time. And concurrency is not an afterthought. It's not something that you use that when you discover that, single-threaded performances turns out to be a bottleneck. It's the way you structure your application. Processes are very lightweight because otherwise it won't work. A single node can run thousands of processes, hundreds of thousands of processes at the same time. They're 100% user level, which is the reason why they're so fast. And I'm going to try to show you how fast they are by running this program. This is a short program which starts n processes, and it times it and prints out how long time it takes. And it's just a short trivial function which just returns OK, but it's still a new process. And you can just use them whenever. They're really small and fast. So let's see if I can get this to continue. The next slide, please. Damn. Let's see. Yeah. No, don't. Please don't. Yeah. Next slide. So now we're scheduling hundreds of thousands of processes. It's important that they can be scheduled efficiently, because if the VM just I'm going to create 100,000 processes and then I can't run them. So Erlang has a preemptive priority-based scheduler, which ensures that each process gets to execute in a fair manner. There's one run queue per core, so each core has its own queue of processes. And perhaps most importantly, it has a work stealing algorithm, which means that if one core is busy doing a lot of stuff and then the other cores turn out to be idle because their processes terminated early, they can pick work from the busy core to make sure that load is balanced. This is usually nothing to worry about. Erlang will just make sure that everything runs efficiently on whatever hardware you happen to have. So, but it's worth mentioning that it's there, and it's very useful and efficient. So now to CRED, which is sort of what I've been doing in the last 6 years. CRED is Klarna's primary servicing system, and this means that CRED keeps track of customer debts and balances, and this means that CRED is a system which knows how much you owe Klarna, and this means that this is like things like data integrity and uptime is extremely important. Because if there is something goes wrong in CRED, then financing people will start complaining where they compare the results in CRED with the banking statements, which tells Klarna how much money is coming into their accounts. So this is extremely important, and it was started as a prototype 20 years ago. It grew to a large, huge monolithic system in 2010 or something, and it did everything like invoices, risk assessment, emails, all of that. And then we started scaling it down and removed stuff, move it out to other systems, and nowadays it's a lean and robust, efficient system, which rarely causes any major issues from a reliability perspective. It survived several drastic architectural changes, and I actually sort of forgot one of the most interesting one. Around 2020, we moved CRED from a data center here in Stockholm into AWS, and this was done without downtime. So this was done during heavy load and without downtime. And this is actually something I almost forgot that we did this, because it was so like couple of years ago. And we've also changed the database backend from a key value store to a Postgres database, also without downtime. And we do daily software upgrades with these hot code upgrades. And the primary enabling technology to make this possible has been Erlang. So Erlang has really helped us to do this. I'm going to cover this a bit short. I think I'm running a bit out of time. I'm talking too much. We have a bunch of different clusters for legal reasons. We have one cluster in Australia, for example, because we're not allowed to store customer data anywhere. So we need to keep local clusters physically on site. And different regions are configured differently. So we provide different products in different regions. They have a Postgres database backend. And the largest one is the EU, which has many terabytes of data. I don't know exactly how many today. Pretty large machines as well. And the North America, Australia, New Zealand, and another small EU cluster are tiny by comparison. And we can run them on your mobile phone, essentially, if you had enough bandwidth. CRED runs 100% in the cloud nowadays in AWS. That means scaling is easy, horizontally and vertically. Well, easy, you know how it is. It's theoretically easy, but it's always a bit hairy. So we can add more machines, and we can switch the instance type to something large. But as those of you who are doing AWS stuff know that AWS can be insanely expensive. So keep track of your costs in AWS, because if you use, this instance type looks really nice, it's really fast, got really lots of memory, but it's expensive. So finding the cost performance sweet spot is really important, and scaling down is as important as scaling up. So when you switch up, you need to switch down when you don't need it anymore. CRED uses Apache Kafka as a real-time event streaming platform, and we process something like 1,000 to 2,000 events per second on average, with peaks going several times that. We have 30 topics and 400 partitions. And this translates to supervisor tree, and this is really effective use of supervisor trees, because the topics here are supervisors and the partitions are workers. So each partition has a single worker, and if the corresponding Kafka broker goes down, this crashes and the supervisor will restart it. And we have API calls, of course, about 500 per second. Yeah, so something which is happens every year is Black Friday. Christmas also happens every year, as we know. Flash sales happen suddenly. We may not even get notified. We just detect that, oh, now this is some store somewhere is sending a lot of traffic our way. Cred relies heavily on Erlang just being able to detect this and adapt to changes in load. And this is rarely a problem. We rarely need to scale up the instances running Erlang. If anything, we need to scale up the instances running the Aurora database backend instead. So this is, I'm coming to the end of the talk, so let's recap the important points. Erlang runs on all kinds of systems, from bare metal to terabytes in RAM and everything in between. It enables you to start with small prototypes and grow them into large production systems. Erlang makes it easy to run your system distributed over any number of servers through features like location transparency, named processes, and message passing. Make reliable and fault-tolerant applications by embracing the let it crash philosophy. Handle errors by structuring your application into trees of supervisors and workers, and let the workers crash and have the supervisors restart them. Use hot code upgrade to load code safely at runtime and transition your processes seamlessly from old code into new code. Erlang is designed with concurrency from the start. This means that processes are lightweight first-class citizens, concurrency is everywhere, and processes become the building blocks of your application. And the powerful scheduler will allow thousands of processes to run efficiently on a variety of hardware platforms. We've seen how the CRED system started out as a prototype 20 years ago, grew into a large monolith, and back into a stable and robust system today. It handles massive volumes of financial transactions efficiently, reliably, without downtime, and with daily software upgrades. It can scale up and down, and things like Black Friday is not a problem. This could not have been possible without Erlang's help. So what are the takeaway points? Erlang is an excellent platform, frankly, to build large-scale, high-volume financial systems on. Erlang was pivotal in Klarna's success, and it powers many other companies today. Key features are scalability, reliability, and massive concurrency. And let it crash. Restart, recover, escalate when needed. I hope to pique your interest in Erlang, and maybe some of you will take the opportunity to explore Erlang when building your next system. Thank you for listening.